Let's talk about a model that's important in medicine. This is called a pharmacokinetic model. Pharma means pharmacy or medicine. Kinetic means chemistry kinetics, like how things move around the body or react with each other. And we're thinking of the body as divided into compartments. So the compartments we'll think about for today, if someone swallows a pill and medicine, it starts in the stomach, then it goes to the intestines, then into the bloodstream, then into the lymph, and then it just decays. The molecules get attacked or changed or whatever, so they aren't molecules of that same medicine anymore. And we're going to say, just for simplicity's sake, that we have 10% of whatever is currently in a compartment moves on to the next compartment at each time step. We'll start with 500 milligrams in the stomach. Remember, I'm not an actual doctor, so check with your real doctor about whatever dosage is safe for you. So let's go do this in Excel. So here I've got whatever's in the stomach, 10% of it moves to the gut at the next time step, but then that means the other 90% stays in the stomach. And nothing can jump straight from the stomach to the blood or the lymph. And we're presuming that nothing gets decayed in the stomach. Just for simplicity, you could put other percentages there. Once it's in the intestines, 90% of it stays there at the next time step, 10% moves on to the blood, and we're taking an approach here like we did on the Leslie matrix and the rental car tracking, where we're saying nu equals current vector times our transition matrix. So it turns out I didn't have to redo any of the matrix multiply because I happen to have the same number of compartments here as I had squirrel age categories here, just by a massive cosmic coincidence. So all I had to do was change the numbers here and the labels. I didn't have to redo any of the math. So what do you think we see? The amount in the stomach is decaying. The amount in the gut goes up initially. The amount in the blood goes up eventually. So I've got the graph saved over here. So the total amount we're keeping track of stays the same. The amount in the stomach falls off, and you might guess that that's exponential, and in fact it is exactly exponential. R squared equals 1, so that's handy. Then how about this curve for the gut? That increases to begin with and then decreases. And for the blood, it increases to begin with, but slower, and then decreases. And an interesting thing here is if you zoom in, this orange part will look kind of linear. If you zoom in, the gray part actually looks kind of like a parabola initially, rather than linear. If you look at the lymph, it technically would look like a cubic. So we've got a system here of like t to the first, t squared, t cubed, each of them times a decaying exponential, and then this one is actually t to the 0 times a decaying exponential, so it's just a decaying exponential. So these are called gamma curves. Here's a formula for gamma curves. It's time to some power times e to the minus t. You can throw a scaling constant in there if you want. And then divided by the power factorial, and that just keeps the total area being 100%. So here's a gamma curve at p equals 0, and then at p equals 1, you can see it's got that linear increase there. P equals 2, you can ignore this part back behind 0. It's got a parabola kind of upswing to it, and then as p increases, the curve gets kind of flatter and flatter, but also longer, and it actually becomes more and more bell curve-like. You can even do it for negative values of p, and there this curve zooms off to positive infinity, but the area under it is still 1, so that's interesting in a Calc 2 kind of way. And these are actually also related to the chi-squared distribution in statistics. So lots of fun stuff going on there, and if you've taken a calc class from me, you've also heard them called surge curves. So not every pharmacokinetic model keeps track of the amount that's decayed, but the nice thing about that is If you do, then the total amount should stay the same, and that's a good way of debugging your spreadsheet. What do you notice about the matrix rows here? Maybe you're noticing that they add to 100%, so we don't have to have everything moving on. You could have some backflow, like maybe 2% moves. Let's say stuff moves from the lymph back into the blood. That's entirely reasonable, but then you'd have to, you don't want to erode a total more than 100% unless you think the body is somehow making more of this medicine on its own. So you can have flow backwards, or you could have it jump compartments entirely, especially if it's in the stomach. Some of it might get decayed immediately. So those gamma distribution curves, they occur in applied probability and calculus and everything. I've been using exactly 10% at each time step, and that's what gives us the gammas. If it's not exactly 10%, then what you get is a sum of exponentials, like a times e to the minus a1t, parentheses around that, we'll do this, plus b times e to the minus bt, plus, etc. So that's a nice, interesting way to think about it. You can do similar stuff for neurons and action potentials, the neuron firing and sending an impulse to another neuron, and these are the names of some of the models that do that. One other thing here, we're doing this nu equals current vector times matrix, which is a very dynamical systems kind of approach to it. Another way to do it is a more differential equations kind of approach, to talk about what delta is and then use delta or the rate of change. So in this next one, let's do that. So I'm going to do my mult here of my current vector with my matrix, Control Shift Enter, and then my new value here is my old value plus the delta value times dt. I'm going to lock the column on that so I can paste it over here, and I'm going to fill delta t down. But we need to think about what my matrix is now. If I start with 500 and 10% of it should move on, is my rate of change of the amount in the stomach really 450? That's going to increase at a massive rate. The 50 makes sense, that the amount in the gut should go up, but the amount in the stomach should go down, not increase by 90%. So pause for a second, think about how I need to change my matrix. Okay, welcome back from pause. What I need to do here is actually have a negative version of that. So whatever I gain in this compartment, I lose from that compartment. And again, I could also have some of the medicine in the stomach going straight to decayed or something. So my matrix no longer has row sums of 1. Now the row sums are usually 0. And let's do this last one here. The amount that's decayed would change by 0% from what it... I'll have to think about that. Let's see how this model goes. Oh, I got stopped by my little note there. All right. So it seems like it's behaving okay initially, but then it's going crazy. So we'll have to think about that. Okay, I found the problem. For some reason, this reference here, this column O, ended up over there, probably because I did a cut and paste rather than a copy and paste. So it's not a math problem, it's just an Excel formatting problem. There we go. So the nice thing about this model is we can use time steps other than one each time, and in fact we can make them unevenly sized, and it still accounts for it.